I'm going to try to answer 5 questions in these 3 videos. In this video, I'm going to define the directional derivative, show how to compute it quickly, and then work an example. In all of these videos, f is going to be a differentiable function of 2 real variables x and y. The derivative of f at a point p0 with coordinates x0 and y0 in the direction of a unit vector u is this number, the limit as s approaches 0 of this quotient. Here are 2 common ways of writing this derivative. df ds evaluated at the vector u and the point p0, and d sub u of f evaluated at x0, y0. Now notice the resemblance to the one-dimensional limit definition of derivative. Also, see how the u is included in this expression. If you change u1 and u2, the limit can turn out to be a different number. One way of interpreting the directional derivative is this. It is the slope or rate of change of f if you stand at p0 and walk in the direction u. Imagine staring down at the xy plane, moving a little in the u direction, and watching whether z goes up or down. Another point I want to make is that you need both a unit vector and a point in order to compute this number at all. But just like in Cal 1, this looks obnoxious. We don't want to compute a limit every time. Surely there's a better way. And here it is. We can compute the directional derivative of f at p0 in the direction of u by computing this expression. The partial derivative of f with respect to x evaluated at p0 multiplied by u1, and the partial derivative of f with respect to y evaluated at p0 multiplied by u2 all added together. In general, this theorem is proved using the chain rule, but we're skipping that here. Here's an example. F of x comma y is equal to x minus y, the quantity squared. We want to find the derivative of f at the point -1 comma 1 in the direction of these 2 unit vectors. First, I compute the 2 partial derivatives of f, and I plug in x equals -1 and y equals +1. I get del f del x is equal to -4 at that place, and del f del y is equal to +4. Next, I substitute those 2 numbers and the components of the vector u into the expression for d sub u of f. I get -4 times 1 over square root of 2 plus 4 times 1 over square root of 2, which is equal to 0. I repeat the process, substituting the components for v, and I get -4 times -1 over square root of 2 plus 4 times 1 over square root of 2. The negatives cancel, and this is equal to 8 over square root of 2, which is approximately 5.66. Just like in one-dimensional calculus, a derivative of 0 means that if you stand at the point -1 comma 1 and walk in the direction of u, you are going neither uphill nor downhill. However, if you turned and walked in the direction of v instead, you would be going uphill, and the rate of change is 5.66. What does this look like graphically? It turns out that f is a special kind of cylinder. We call it a parabolic cylinder. Here is one view of that cylinder. In this graph, the positive x and y directions are both coming towards us, and the positive z direction is upward. For clarity, here is another point of view for the surface. I've also marked the point -1 comma 1 on each graph. Here are the 2 vectors u and v again. Both components of u are positive, so the vector should be pointing towards us. On the other hand, v should be pointing roughly to the right because it has a negative x component and a positive y component. I will label those 2 vectors. The green vectors happen to be lying on the surface, but the gold vectors actually are underneath the surface. You can imagine, especially in the right-hand picture, that if you were standing on the white dot and walked in the direction of the green arrow, you would not go uphill or downhill at all. On the other hand, if you walked in the direction of the gold arrow, you would be walking uphill.